Hey, good morning, students. And today we'll be working on another types of uh, unsupervised learning, and that is a dimensionality reduction. And the idea of dimensionality reduction is as the name suggests, we're trying to find a way to reduce the dimensionality so that it can be visualized, or maybe we can have better representations of that features. So that is the idea of dimensionality reduction. In the areas of deep learning, for example, we got something like autoencoders. That is also one type of one kind of algorithm that helps us do dimensionality reduction. But anyway, today we're working on machine learning, the traditional classic one, and uh, uh, particularly we will be working on the principal component analysis. And trust me, there will be a little bit of mathematics, but I will try to guide you through. And if you understand something like Lagrangian, then things will be much easier because the principal component analysis will involve in that too. But anyway, let's start. So in principal component analysis, the idea is we want to define, we want to reduce the dimensionality. So the first thing in any scientific problem, we want to frame the problem clearly first. So let's say I have a xi, right? I want to, and let's say this xi has a dimension of n, right? Let's say n is 5. But I want to reduce this 5 to something like less than 5, right? Like something 4, 3, and I call this n prime. So how do I do that? Well, if we study linear algebra, we can try to just find some projection matrix P, in which when it dot product with xi, it would transform this into some dimension in the plane with n prime features, right? So this is a very nice way to frame the problem, that we need to find this projection matrix. But of course, if xi is not only a single sample, but it's a matrix of samples, then the problem remains the same. That is, we need to find the projection matrix P that can transform a lot of samples of x into n prime, right? And if we try to dissect it out, the shape of B is nothing but n comma n prime, right? Because x is m comma n. When you dot product, this n will be cancel one another, and there will be only n prime left with the m. Hence m times n prime. Yeah. So I think as a teacher for many years, I think understanding how do you frame the problem is one of the most important skill you need to have, right, as a scientist. But anyway, if you understand this, you are already 50% good to go to understand PCA. The rest of that is basically the approach. If you don't feel comfortable, you can pause my video, but don't worry too much, all right? The idea is just to find this projection matrix. So now, the next thing is, okay, we frame the problem, and the problem is very clear that we need to find this B. If we make this as an optimization problem, which we are very, as mathematicians are very good at, we need to define what is optimal, right? So for example, this is that this data is lying on the 2D plane. So you can say that each x has 2 features, right? So in this case, n is 2. But let's say I want to define n prime as 1. That is, I want to change this 2 plane data into just one plane, right? So what do I mean by 1D? Well, I just want to put everything on just one line, right? That is the idea of 1D, right? So you can see that there's so many ways I can, you can see that there's so many ways I can put my data into one line, right? And every time this axis is moving, that is just how we can define B, right? So there are so many B. You can see this is B, this is B. So there's infinite number of B's, right? But which one is the optimal B? if we can define this, then we can set up as maximization problem, and then we can use our favorite derivatives to solve this problem, right? So if we see this clearly, I think we can all agree that this is the best line because it is able to capture the variance of the data, how the data is spread, right? I think for those who don't understand what is variance, you can imagine, right? If these are the data, and instead of drawing, so I want you to compare between this line and this line. If I draw just two lines, I know there are so many lines. Which line would be the best? Well, if I draw this line, things will be mapped in this way, just like the red dots currently. But if I draw this line, the things will be cluttered in around here, right? Because the mapping will be just map perpendicular, right? So you will lose a lot of information, right? So the idea of maximizing the variance means that we, even though this is a 2D information data, we want to map to a plane in which it keeps the original information as much as possible. Of course, we're gonna lose information, but if we can keep the variance as much as possible, then that would be great, right? So this is the idea. So how do we? So now we need to find the B, and we now already defined that to find what is the best B. The best B is the one that maximizes the variance of the data, right? So now the next thing we need to do is how do we find the variance, right? So so here we would say that PCA is a dimensionality reduction algorithm that maximizes the variance by finding a matrix B. Okay, So now let us define the variance, right? So the variance of Z1. So what is Z1? Z1 is basically this line, right? The line that we want to. So basically, after we project Xi to Z, this is the variance, right? So how do we find the variance of Z? Well, according to the formula, we know C is the variance is nothing but just taking the Z minus the mu, and then square them, and eventually you'll get the variance. Well, we can make this formula a little bit simple if we just delete the mu. How do we do that? Well, we just center the data. So instead of this, we just center the data here, right? That can be done. We just do some normalization method before we do anything. Then that would be okay. So now the formula is very nice. So now we can now define that Z1 is nothing but B1 times Xi, right? This B1. Well, this is the projection vector, one of the vector so basically this one is nothing but this one, right? But we just take one of them, right? You can imagine B has a lot of dimensions that translate Xi, but we just take one of them, right? And then that would translate in that features, okay? So that is the way we can write this. Now, if we substitute this information into this formula, so you can see that Z1 is now this one, and then you do the square thing, you get this thing, and then if I extract the Xi only and B1 and Bi here, I will get something that looks like this, sorry, right? In which S is nothing but the covariance, right? So if you remember, when you multiply X, and because the mu is 0, is basically, this is basically covariance, right? Because without the mean, then this is basically the covariance, right? And you can see right here, I say that S is nothing but the covariance matrix. It may not be look the same covariance matrix that you are aware of, because simply because I already centered the data. So that's why there's no minus mu So for those who are not familiar with covariance, it's basically x minus mu, and then multiply with x minus mu, right? But because there's no mu, it's basically these two multiply with one another, right? So that is just a recap, right? And finally, if this is a matrix form, then we just it's nothing but just the matrix transpose X. Okay, great. So now we find that the variance of C1 is nothing but this formula, right? And what do we need to do? We need to find a way to maximize this. So we need to find B in which it maximizes this one. All right. So how do we do this? Well, we can see that that there's some constraint here. I said, right, in which the vectors that in which I want to project on, I want to make sure that is a unit vector. All right. There's a lot of things, but anyway, the unit vector idea is basically the idea that we don't want to use the magnitude to make our variance bigger, right? So we want a vector, basically a projection matrix that doesn't change the magnitude of the variance, right? So that's why we want to make sure that the projection matrix is just a unit vector. So when we project X, it doesn't change any like variance or magnitude of anything, right? So that is the constraint. So because this is a maximization problem and there's a constraint, you can revisit the SVM tutorial, and we need to use the Lagrange method, right? In which the Lagrange say that if we want to optimize anything, we just take whatever you want to optimize right here, plus some inequality conditions, like if GW is some constraint that is less than or equal to 0, and HW is any condition that is equal to 0, right? In this case, ours is equal to 1. So we can define our problem like this, right? We want to maximize this one. So we want to find B1 that maximizes this one because this is our variance. And we want to make sure that this vector is a unit vector. So in this case, we can write our Lagrange our formula in this way, in which B1 plus it. This is the FW for those who don't understand. And this one is just the HW. The reason why we have 1 minus is because we want to make it as an equation equal to 0. So now we got this formula, right? So if we revisit the Lagrange, we need to find the partial derivative in respect to B1 and beta. And these are the answer. So I skip it and make it very quick, right? And if we set the partial derivative equal to 0, we'll get this information, right? So what does this mean? If we look closely, this is basically the answer, right? And the answer is basically saying that, hey, if you want to find the B1 that maximize the variance, the B1 must be the eigenvector of this S, right? So what do I mean? You can see it's a matrix that multiply with some B1 is equal to still B1, but the beta change, right? So I know this is something that for those who recall what you study in the in the bachelor degree, we call B1 as an eigenvector of S, right? Because when S dot product with B1, the direction doesn't change, right? But the magnitude actually change, right? So we call that B1 is the eigenmatrix of S. So this is the whole story, right? That is by doing Lagrange, it tells us that if we want to find the matrix B1, the vector B1, we just simply find the eigenvector of S. Yep, as simple as this. Of course, for those who are not familiar with eigenvector, eigen whatever, you don't need to worry too much. You just need to understand. For those who are confused, you just need to understand that, hey, we got the problem and we want to maximize this variance. And I hope that you agree with me that variance is a good way to define that B. And then we just set up the equation, what we need to maximize and what we need to subject. And if we don't do this, then when we project B1 to xi will become too big, right? Which is not okay. So we want to make sure one is a unit vector. So if you understand this, then that's fine. And when we plug in into some strange formula called Lagrange, and now we got this answer. And basically, we need to find B1 such that when B1 dot product with S, you still get B1, but the magnitude change, right? So that is the idea. But in mathematical terms, we call this eigenvector. All right. So that's that. That is the whole idea of PCA. That is a eigenvector of S, then we can find the B1, right? But for those who really want to understand what is eigenvector and eigenvalue, right here, you can see here what I mean by eigenvector, right? So you can see this is the matrix S, right? And you can see whenever I apply with this some vector, the blue one did not really change the direction, right? So you can see that this is the eigenvector of this matrix, right? But you can see that this one changed the direction, right? The blue does not change the direction. So we can say that blue one is the eigenvector of this matrix S, okay? So, but anyway, I think that is even over also, it may satisfy some people, but it may not satisfy those who are mathematical savvy. Then review all the things you learn in your bachelor degree, which I will also skip how do we find vectors, but in simple, there's a formula. We know that every matrix be decomposed in SV Q matrix the Q, and then that would be our eigenvector, right? And here I'm just showing you how do I get the eigenvectors. All right, so I think then how do we actually get the line? Well, once you get the B, you just take the Q from the eigenvector and then just dot with X, you already get the Z, all right? Okay, great. So hopefully that is not too much of mathematical details. Definitely, if you are not comfortable with mathematics, you can pause my video and look through the tutorial again, and maybe ask ChatGPT maybe what is eigenvectors, etc. But anyway, the idea is that, right? Great. So let us take a look at code, and hopefully we can better understand this. So here I already prepared some code here, and I think I got NumPy. Give me 1 second. Okay. Okay, great. I think I have one NumPy here. So just give me 1 second. Maybe I delete this. Right, so this is my basically my data, right? And the X is just a 2-dimensional, all right? So now I want to project it into just one axis. That is that, right? So what I can do is I want to define my function called PCA. And the first thing is I want to center my data. Number 2 is I want to find my covariance S. And number 3 is I want to find my eigenvectors, right? And associate eigenvalues. Eigenvector is the B1, and eigenvalues is basically the beta here. It's basically this one. That is once you take the S and rotate it or whatever, stretch it with B1, now the main magnitude change, and that is the B beta here. The beta is the eigenvalue. Yes. All right. And what else? We want to get the k largest eigenvectors, eigenvalue vectors with, okay, I should say get the eigenvectors with k largest eigenvalues. So how many k I should do? Well, if your n prime is equal to 5, then k should be 5, right? That is, those are the 5 vectors that maximize your variance, right? But if your n prime, in my case, mine is 1, right? So k should be 1. That is, I just get the largest vector eigenvectors. Yep. Okay, great. So what else we need to do? And of course, we can project the new vector, right? Now we can get the thing. All right. Okay, great. So I think that should be it. And this is the algorithm. Basically, there's almost no training. You just find the covariance, get the eigenvectors, and that is basically the way you can project the data into those dimensions, right? Please note that this algorithm can work in any dimensions. Okay. So now let us center the data, right? The center data is super simple. We just take the mean, and then now mean is big, and this is a good way. All right. So how do we find a covariance? The covariance is nothing but because it's a center, you just multiply it itself and divide it by m, right? As we already defined up there. Now, how do we find eigenvectors and eigenvalues? Well, we just send in this covariance. So we want to find the eigenvectors and eigenvalues of this covariance. So we're just going to use a function called from the linear algebra library of the NumPy. And now we got eigenvalues and eigenvectors. Now we just want to get the, so first of all, we want to sort all these eigenvalues first. So now we got that number, right? And then what do we want to do? Well, we just want to make sure that, of course, if n components is larger than the number of eigenvalues, something is wrong. So you can see that this is, what is n components? N components is basically the dimension I want to project to. Here I define 1 because I want to change 2 to 1. So how many of eigenvalues I want? Well, eigenvalues is basically I take those index first. So first I project it into that, and then I just take that many. All right. So this is a very, very straightforward. Finally, I think I should print here, right? How about I think I forgot to print, right? I should print something. So eventually things will be great. So this is, I print the covariance. So later on we can take a look. And here I also print the eigenvalues and eigenvectors so that we can see. So eigenvalues, the shape is n. And eigenvectors is n comma n. Okay. And if you will forget the y is, the shape is n, you just go up and take a look at the problem framing, and you can see that eigenvectors, the projection matrix, the what, it should be n, right? Yes. Now what do we want to do? We want to project our data to the new vector. All right. Using the eigenvectors, right? So how do we do? Well, if we go all the way up, I told you that once we find a projection matrix B, we just simply XB, right? Then because we already defined the B, that B is the eigenvectors. So what do we do here? Well, we simply multiply them, and that should be done. Now we got the new X that is only one dimensional. X at eigenvectors. All right. And then I think that should be it, right? And this function, it just return the eigenvalues. and eigenvectors and projected X. All right, so hopefully things are done. So that is PCA, right? I think for PCA, the only thing that is difficult is that you are not familiar with eigenvector. But if you just spend maybe 10 minutes, 20 minutes recapping, that should be no problem. Yep. All right, so now ready to use our thing. So what we can do, well, we can call this function PCA and already, let me just check whether I have X. So I got this X and a huge number. So I got 200 samples. So what do I do? Well, I want to call this function PCA, right? And it will return this one. So I'm just gonna copy this, equal to PCA X, and then how many components I need? N components equal to 1. And that is done, right? So what do I get here from this PCA? Well, this is a covariance matrix. So if you recall, this one is a covariance in the x-axis. This is a covariance in the y. This is the variance of x. This is variance of y, and this is the covariance between x and y, right? But anyway, it means the variance of x is quite much, right? As you can see in the picture, right? In the x-axis is very spread, but in the y is not so spread, right? So hence this number, right, which is not so small. But you can see the covariance between x and y is positive, which makes sense because it's in the positive direction. So that is the covariance. And now once we take that, we find the eigenvectors. So we can print out the eigenvalue, right? Now we can also print the eigenvectors, right? So this is the one vector we define, right? That is that can project our x into one dimensional, right? Great. So let us see the projected x look like. All right. It's very messy. So why don't we just plot this into a vector, right? So I already prepared some code. It's a little bit long, so I just let me just delete this one. It's a little bit long, but there's nothing important here. It's just a function to plot everything. And then so, oh, of course, there's something here you can read here a little bit. How do I plot? And then, okay, it needs the mean too, right? So I think I need to return the mean. Otherwise, I cannot plot properly. The mean is important because so I know where does it come from, right? So I need to return the mean, and here I want to take the mean. All right. So I clear the outputs, restart run all. All right. So this is the original data, right? And but I think okay, perhaps that could work. Yeah, because in the scatter plot it wants a two-dimensional, right? So I think I need to put 2 anyway. By the way, you can do just 2 1 and you can already get the x, right? But this is just for the plotting purpose so that we can understand what is happening. All right, so I think that should be it. Yes, okay, great. So you can see that this is the data, and we find every data we can find. If the data is two-dimensional, we will always find 2 eigenvectors, right? This is the first eigenvectors and the second. And based on that, we find that this eigenvectors is the number 1 with the highest eigenvalue. This means that if we dot this one with this data, this will give us the one-dimensional vector that yield the highest variance, right? So I take this vector. What is this vector? This vector is basically this vector, right? This one, right? Minus 0.9, right? So you can see that it's negative here, right? Now, once we projected it, now the data looks like this, right? Even though this is a 2D plane, you can imagine that everything is already lined in 1D, right? But of course, this is now I'm plotting in 2D, but actually everything is in 1D, right? So great. So I think it's PCA. Hope understand. After listening to my tutorial, I think you can now better understand what is PCA. The idea is you frame the problem, find a projection matrix, then you define what is optimal, and that is maximizing the variance. You put it into optimization method. You find out that the best the best vector B1 is nothing but is an eigenvector of S. Then I think that is the whole story. But of course, if you want to understand what is eigenvector is something that when you is a projection matrix that when it multiply with any matrix, it does not change the direction. In this case, this blue arrow is a projection eigenvector of this matrix S. Stretch, the blue arrow still remains the same. Eigenvectors is very important. It's like physics, gaming, right, etc. All right, thank you very much, and see you in the next tutorial. Bye-bye.